So those were the methods to solve a system of equations if it has an intersection point. Some pairs of lines don't. Why wouldn't two lines have an intersection point? Well, if they were parallel lines, right? Parallel lines by definition don't intersect. Looking at two lines in slope-intercept form, it's pretty easy to see that they're parallel. They just have the same slope, but different intersections of the y-axis. And they therefore won't have a solution. But what if they're not in slope-intercept? Well, let's solve using one of the algebraic methods that we know and love so much. But if we know that two lines are parallel, like I'm telling you right now, these lines don't intersect. They really don't. How can we use these methods if our original assumption is false? Easy. Just do it anyway, knowing that it'll fail. I've been doing this stuff, systems of equations, since I learned them in middle school. But why this method works wasn't really clear until I got to the upper level classes of college. This is called a proof by contradiction. You know, like when you're on a homework assignment or a test problem, and it's a kind of a long problem. There's a lot of different steps, and then, you did a good job, you show your work, and, well, you get the wrong answer. Terrible. I know. That's okay, though. You can just go back in your work, find the mistake, change it, and then continue on. We are going to use that method of correcting our work to our advantage. We are intentionally going to make a mistake from the beginning, assuming that something is false, then do the work as normal until we get to something that's completely absurd. Whoa, wait a minute! I mean, that's not true ever. So we use the same method, we go back through our work until we find a mistake, and assuming we did all of our actual working out properly, the mistake that we have to come across is that original assumption, the one that we started with. We assumed that these two lines had an intersection point. Long story short, if you try to find an intersection point of two lines and you come to a conclusion that is never true, then there is no intersection point, which means that they're parallel lines. And to answer this question, you would say that it has no solution. Here's another problem that you might run into. You could do the work necessary to find an intersection point, and we find a statement that is true. Like, always true. 0 always equals 0. Every single time. But hey, we didn't find an intersection point. Like, we didn't find a singular x and y. But then we also didn't run into a contradiction. Like, we ran into a true statement. So, what is it? You have the same line twice, but they're sneakily written a little differently, just to confuse you. Mwahaha. So if you think about it for like a second, with concurrent lines like this, you realize that every point is an intersection point. That's why there's no single intersection point, but you have a true answer. Because no matter what you put in for x and y, it's going to be an intersection point. All of the points are intersections. You would answer these questions by saying infinitely many solutions. Now, your teacher might tell you the term for this type of system is called consistent, and this type of system is called inconsistent, and this one's called dependent. To which I say, why give students unnecessary amounts of vocab words to describe something that you already understand?